So our next speaker is Phil Kaszuba, and with the Global Foundries senior member of the technical staff, lead engineer in their SPM laboratory. They do a lot of analysis on, of course, state-of-the-art semiconductor devices and nanostructures. So Phil is going to talk about meeting the challenges in analyzing state-of-the-art semiconductor devices using SPM. So Phil?
Okay. Can everybody hear me okay? Yeah. Okay, good. Yeah, I'll go.
More for recording. Oh,
yeah, we're all set there. So, okay, good. First of all, thank you, Rigoberto, for the introduction. And I would also like to thank Keybuck and Park Instruments for giving me the opportunity to come here and speak with you all today. I look forward to this opportunity. I'm going to talk about semiconductors. We're going to switch back. Alan gave a nice talk a little while ago about some of the challenges meeting the semiconductor industry, and I'm going to continue that discussion a little bit with some of our experiences up at IBM, which is now Global Foundries, and my experiences throughout a few years in the area of semiconductors, and how Scanning Probe Microscopy has played a critical role in the evolution of semiconductors from one technology node to the other. The industry very aggressively wants to move forward to the next technology node, making devices smaller, making them faster, making them more efficient. So now we can hold more computing power in our pocket than what fit in a whole room 20 or 30 years ago. So it's very aggressive. And as a consequence, the analytical instrumentation that helps us through technology development, from the initial technology conception to development to manufacturing, to the necessary evil of failure analysis. I mean, the instrumentation in support of these technologies has had to keep up at best with the technologies, such that we can keep the industry moving forward at its aggressive pace. So I'm going to concentrate on how we've met the challenges in analyzing state-of-the-art semiconductor devices with a concentration on scanning probe microscopy. This is a chart. I show this picture a lot, never get tired of showing this one. This is where it all started. Back in 1980, Gerd Binnig and Heinrich Rohr, two researchers in the IBM Zurich research labs, invented the scanning tunneling microscope. They applied for a US patent 2 years later. 2 years later, they got a US patent for that. 1984, 4 years later, they were awarded the Nobel Prize for this invention. Incredibly simple instrument. But in 1986, Binnig and Christoph Gerber from the University of Basel and over in Stanford, Kelvin Quate. Thank you. Kelvin Quate, who has a somewhat intimate relationship with Park Instruments. Okay, they went on to invent the atomic force microscope, which has evolved into the instrument. Well, it's the reason why we're all here. This is an overview of what I'm going to talk about. Okay, first, I just want to give a little bit of overview of semiconductor devices. The field effect transistor, the fundamental building block for basically virtually all of the electronic devices that we have throughout our lives today. So I want to talk a little bit about just the field effect transistor, and then I'm going to talk a little bit about microscopy in the semiconductor world. Virtually everything in semiconductor design, fabrication, analysis is done under a microscope. Okay, and that microscopy has had to evolve rather aggressively to stay up with, or at least try and keep up with the advancement of the technology. I want to talk a little bit about progress in the semiconductor industry, basically kind of a historical perspective. Okay, devices, which were state-of-the-art a few years ago. I mean, semiconductor companies are bragging about their 1 micron devices. I mean, that's long since history. But even back then, there had to be technology to analyze these structures, which at the time were state-of-the-art. leading us to where we are now. Ellen had talked a little bit about the FinFETs, the 14 nanometer, next generation technology, 7 nanometer. Okay, we have to have methods to analyze these technologies. I want to talk a little bit about some of the work that we've done up at my facility in Essex Junction, Vermont, in my lab, where we've actually done some analysis of metrology for the 14 nanometer node. In particular, carrier profiling. Jocko had the question about carrier profiling in the FinFET devices. Using what potential technique. Alan talked about scanning spread resistance microscopy. I'm going to talk a little bit about scanning capacitance microscopy, a method which we've successfully employed in analyzing these state-of-the-art 14 nanometer devices, and with some food for thought on how we're going to make it to the next generation technology. I'm going to talk about an actual case study. This is new data. I mean, this is previously unpublished data that we just recently got over the past few weeks on an individual case study. One of the challenges facing the failure analyst who's got to look at one individual device, one individual fin, and determine what the root cause for the malfunction in that fin is. And that's incredibly challenging. And I'm going to talk a little bit about an analysis that we had done on one particular fin, and then we'll just hit with some closing statements, concluding remarks. So let's talk about semiconductor devices, going from 2-dimensional to 3-dimensional. First, what I want to do is just give a quick overview of the classic semiconductor field effect transistor fabrication process has been. Because then it'll help you to understand the challenges that we've faced over the years in analyzing these devices. Okay, so we start out in this case with p-doped silicon, boron-doped silicon, a silicon substrate, and we're going to systematically, step-by-step, build these transistors. And the way that we do that, we're going to implant arsenic and phosphorus or boron to create wells where the different polarity devices are going to ultimately reside. And then oxidation step, we grow or we deposit a little polysilicon strip, which is where we're going to apply the charge, which is going to turn that device on or off. But these are some of the critical steps here. Okay, after we've got our polysilicon in place, the doping steps, where we actually do the final steps in forming that switch. Because ultimately, in the finished device, in this case of an N-channel device, we're going to have P-type silicon here in the middle and N-type out here. And what we're going to do is we're going to put a charge in it and invert that area in the middle. Okay, so it all becomes N-type. Okay, so we've got basically this area electrically connected to this area by placing a charge on this, what's called the gate. Okay, that's just a quick overview of what the PFET and the NFET are. They're different polarities. One would switch on with a positive polarity, other one would switch on with a negative polarity. They're basically just an on-off switch. That's it. And when you add, hundreds, thousands, tens of thousands, millions of these, now you get functionality out of a chip. And when you put these out in certain circuits and configurations, now you get functional chips, which we're all accustomed to. But the really important steps, or some of the most critical steps, are the implants that form these diffusions here. Because if they're not in the right place, if they're not in the right concentrations, that device may work, but it may not work properly. Okay? And if it's not working properly, take one device out of, say, a few million in a chip can render that whole chip non-functional. And that's kind of important when you're in the semiconductor industry and you're cranking these things out and you want them to be good and functional. So, as a consequence, we've had to develop techniques over the years to be able to look at these devices and analyze them. Way back, it used to be chemical analysis. You take a chemical that was mixed that would preferentially etch different doped regions and then look at them in an SEM. Well, that worked great with large devices. But as technologies continued to shrink, you couldn't use that method anymore. It wasn't accurate enough. So now what are we going to do? Well, here, okay. I wanted to talk a little bit about the three-dimensional devices too. This is what we've got now. Okay, where we are today, the FinFET. Alan talked about the FinFETs a little bit. Okay, the FinFET is a three-dimensional device. The devices that I just showed were considered two-dimensional or planar devices. Okay, so you've got a long strip of polysilicon, put a charge on it, turn the device on or off. Now, what we've done is we've got a fin. You've got a vertical fin of silicon, and now you've taken that gate material and you've wrapped it around the fin. Okay, we're now making these devices, and this is a recurring theme: smaller, faster, and more efficient. Okay, I mean, if we can make stuff smaller, but it's not faster, why bother? If it's not more efficient, you can make stuff smaller and faster. If it's not more efficient, well, you're still going to need a giant battery to power it. So you need all of those. You need a combination of all of those with each successive technology node. So now we've gone to these three-dimensional devices. Okay, so basically we've got this gate material wrapping around the source and drain. And we're able to make these things a lot smaller using the process that Alan had shown. It's a very, very complex process to build these devices. But it accomplishes the objective. Okay, now just want to give a brief overview of the microscopy in the semiconductor world. What are some of the different types of microscopy that we were using and are still using? But where do we need to go? Okay, so this is just a, kind of a length scale comparison, and looking at packaged chips. There's various forms of acoustic microscopy. We're looking at a very, very macro scale. For analyzing something that's in a package. Okay, but as we progress to smaller and smaller scales, we need to employ different types of microscopy. And once we get all the way down here to where we are now, actually this is where we were a few years ago, down in the single nanometer angstrom range, okay, we've had to employ largely transmission electron microscopy, TEM, and the scan probe techniques, SPM, AFM, and some of the other techniques that are employed for analyzing these devices, which have gotten so small that the traditional methods no longer work. They don't have either the lateral resolution or the ability to resolve different materials. For various reasons, these other types of microscopy, SEM becomes difficult. I mean, it's progressed quite a bit, but still, in order to get down in the scales that we're at now, we need to rely on the scan probe techniques and TEM. And this is just a little bit more on why scanning probe microscopy has lent itself so well to analyzing the latest technologies, because everything's gotten so small. Okay, here, optical techniques, you still need. You still need for looking at devices in a macro scale. Well, which is a macro scale now, really. Okay, but SEM is employed quite a bit, but we're really relying on TEM and SPM. Now, there's one pretty significant factor between TEM and SPM, and that's right here. Typical TEM we're looking at nowadays, you're looking at 3 million and up. SPM is still, for a full-blown scanning probe microscope, we're still looking at under 500K, which is important. That's important when you're in an analytical lab buying equipment. Are we going to can we afford to populate our lab with a room full of TEMs, or do we try and adapt this approach, which is much more cost-effective? And likewise, I mean, there's other advantages. Now, these two techniques complement themselves very well. I mean, we in our lab work very closely with our TEM lab, okay, because there are strengths and weaknesses to each of the techniques. So we work together very closely. But that being said, the SPM and its associated techniques have lent itself very well with its ability to resolve features at a very small scale and look at different properties of materials, material properties, electrical properties, and there's a whole plethora of different types of techniques that have evolved. Right from that first scanning tunneling microscope or the first AFM that they constructed at Stanford. So a lot of advantages to using scanning probe microscopy for state-of-the-art semiconductor device analysis. This is just a brief overview. I mentioned there's a lot of different methods that have been developed on the scanning probe microscope platform over the years. And this is just a small sampling. But this is a sampling. These are the techniques that we use primarily for semiconductor device analysis. Of course, we apply atomic force microscopy for virtually every analysis we do. And then scanning Kelvin probe microscopy, I'll talk a little bit about that. We used that earlier, in the early days, for carrier profiling. It was a very effective way to do that on some of the larger devices. Scanning capacitance microscopy, I'm going to talk a little bit about that. That's the workhorse technique that we've been using lately for carrier profiling all the way down into the 14 nanometer technology node. And then there's conductive AFM for looking at electrical properties, magnetic force microscopy, which there are applications in semiconductor analysis as well. And then a technique that we developed in our lab, the scanning surface photovoltage microscope, which we have used for analyzing stress on a nanometer scale. All right, progress in the semiconductor industry. There's that constant drive, and here comes that theme again, smaller, faster, and more efficient. Well, let's go back, 1992. 1 micron planar FET. Remember, IBM and Intel, man, this is the coolest device that we have made. It's small, it's fast, it's 1 micron. Okay, and this is an image that I took back in '92 on one of the IBM prototype AFMs. I had the opportunity to work with that instrument shortly after it was released from one of our research labs. So this is an image at silicon. I've basically removed all of the materials, just showing the bare silicon. And if you remember back to that cross-sectional view I showed of the FET, the important areas are what has been implanted and diffused down in the silicon. So, what I do, chemically delayer this, okay, and we're looking at silicon here. Now we go to 2000. We've got the quarter micron planar FET, done the same thing here. Okay, but this is the progression that we've made. Okay, so 8 years later, we're down to quarter micron. Now we go in year 2009. Now we're down to 90 nanometers. And I'm trying to show these all on the same scale. This is where we are now. 2018, 14 nanometer FinFET. This is a cross-section, TEM cross-section of the FinFET, and this is what we're talking about here. 14 nanometer FinFET, it's a three-dimensional device now, so that this is the actual fin right here, and this is the gate area. Well, using the lattice constant for silicon 5.43 angstroms, this device is only 26 atoms across. Okay, we've come a long way from this guy down to where we are here. 392,000 atoms total. In the total volume of this device, 8 dopant atoms. Using a normal a dopant concentration of 1E or 1E18, there's 8 dopant atoms in that. How do we analyze? Okay, now just going back to this early device a little bit, and I mentioned this device has been deprocessed to the silicon level. This was some work that we had done back in '92, '93, where we used scanning Kelvin probe microscopy to image this device. And this was kind of earth-breaking at the time, because we were able to using a non-chemical technique, we were able to image this device, and we were able to understand where the N-type silicon was, where the p-type silicon was, and where some very specific features were in this device. Yeah, it's a very noisy image, but it got us into the next phase of where we needed to go in terms of device analysis. So let's talk a little bit about how carrier profiling in semiconductors has progressed. You know, I talked about the importance of knowing where the dopants and where the carriers are in the finished device. Here we are, scanning Kelvin probe microscopy, using a non-contact approach there. And now with this quarter micron device, we transitioned to scanning capacitance microscopy. I was very fortunate to work with one of the inventors of the scanning capacitance microscope. And what we did was we developed this technique into a much more user-friendly technique, and actually developed the instrumentation so that it worked, you know, a signal-to-noise ratio, lateral resolution, and so on and so forth. But I mean, this here, I mean, this is a lot smaller image, but it's even so much cleaner than what we were able to do using scanning Kelvin probe microscopy. And by the way, there's also something wrong with this device. You know, this is a p-type silicon, n-type silicon, and over here we've got it's called punch-through. So we've got where silicide is basically punched completely through the p-type area. That device is going to leak, which is okay, but if you've got a few of these devices on your chip, okay, that chip's going to use a lot more off current, off power, and it's going to drain your battery. You don't want that. Now we go to 90 nanometer, scanning capacitance microscopy again, and I've enlarged this image, but we're still getting some pretty good detail here, n-type and p-type regions. Here we are at 14 nanometer. What do we do? I mean, will the existing analytical methods and sample preparation methods work? We don't know. So let's talk a little bit about analysis at the 14 nanometer node and beyond. With respect to scanning probe microscopy and atomic force microscopy in the fab, AFM is primarily used for dimensional analysis. In our analytical lab, scanning probe and its associated techniques for dimensional analysis, dopant or carrier profiling, electrical analysis, and we're also using it for strain analysis as well, using scanning surface photovoltaic microscopy. So it is in widespread use in both the manufacturing fab and the laboratory. Carrier profiling and FinFET. I talked a little bit about this early on. You know, why is it important? Okay, and it's providing critical data, you know, for right from technology development all the way through to, you know, end product failure analysis. And how are we going to do that? How are we going to do it? I posed that question a while ago. How do we do it? There's atom probe tomography. You know, taking your sample and fashioning your sample into a field emitter, and then basically using that, you know, the material that is emitted from that sample on time-of-flight sims and reconstruct it. Okay, really neat approach. It doesn't lend itself very well into a analytical lab environment. The sample prep is very, very difficult, and when you've got a one-of-a-kind sample, this can be a problem. Sims, you know, great analytical method on large structures. But the scanning probe microscopy techniques show promise. But this is something, the 14 nanometer technology has been in full production for a while, and we need it. We need it now. I'm not going to get into too much detail with regard to scanning capacitance microscopy, but suffice it to say that it is the analytical approach that we've attempted for disclosing carrier profiling on state-of-the-art technology. Okay, so now, with regard to FinFETs, again, they're three-dimensional devices. It requires three-dimensional analysis. Now, do we analyze in plan view and do a tomographic reconstruction, or we do look at these cross-sections? We don't know. But we do know that in cases we're going to need to characterize a single fin. And those fins are 14 nanometers by 14 nanometers at their critical dimension, at their smallest dimension. Okay, so 26 atoms by 26 atoms. This is some work that we've done in plan view using scanning capacitance microscopy. This is a topographic image, okay, where we've basically mechanically polished down into the fins. So these bright areas, these are the actual fins. Okay, and we've got a series of NFETs, PFETs, and more NFETs. And this is just to revisit our 3D representation. This is a carrier profile of that same area. And this image is very encouraging. I mean, this was one of the first images that we got looking at plan view fins. And very clearly, I mean, we're seeing our p-type and n-type regions. But that begs the question, where are we? Where are we in this fin? We don't know. Well, I mean, we did know with this one. You know, I mean, are we up here, here? Where are we? And in this particular fin, this is where we were. We're down here. Okay? And the really critical area is up here. But nonetheless, very encouraging data. This is what we really need to do. Start up here and work our way down sequentially through that fin, and then do multiple images, multiple topography and dopant or carrier images, and then do a tomographic reconstruction, giving us a three-dimensional representation of the device. Now, I mentioned a little bit about a cross-section, some cross-sectional work that we had done. I want to talk a little bit about a case study here. Again, here's our representation. Here's our fins right here. And this is the gate region. So we've cross-sectioned into this area here. In this particular device, we had a P-channel device, a P-channel fin that would not turn off. We couldn't get the thing to turn off. This is the electrical data that told us it was that particular fin. This is what it should look like. This is an FinFET, but it should come down here to a nice low current level, and this one was not. It would not turn off. Something was keeping that device from turning off. Now, we had to go in and look at, well, this was narrowed down to two fins. This particular device was comprised of two fins. This is the layout data here, and basically this is the fin, or this is the gate right here. Our fins are going in this direction, and we knew that the problem was either here or here. How do we get to that spot? Because this is a one of a kind. If you process through it, the analysis is over, and all of the work that was put into this thing leading up to that is all for naught. So what we did was we polished into it from this direction. Oh, and by the way, the RMS roughness when we get to our cross-section surface has to be less than 5 angstroms RMS, or else it's going to put a lot of noise into the data with scanning capacitance microscopy. So we did that. We polished into it. We performed atomic force microscopy, scanning capacitance for carrier profiling. We also did what I call a voltage spectrum. Now, this is the first time that these images have been seen in the public. Okay, here's our N-type fins, and here's our P-type devices. So our source and drain goes in that direction, and lo and behold, there's a little spot right there in one of the fins. Okay, and the way that we got there was, I mean, it was a long iterative process. Basically scrape off, polish off maybe a layer or two of atoms, and then it would go back in the AFM and do topography, dopant profiling, then come back, another couple layers of atoms, back and forth, back and forth. This went on for 3 weeks until we got to the area of interest. And lo and behold, we found a defect site. Now, at first look, it tells us there is an accumulation of arsenic and phosphorus in that area. But with one picture, you can't really tell that for sure. You need to take a series of pictures. And so what we did a voltage spectrum on this. And what I did was applied a series of different bias conditions that force these devices into accumulation and inversion. Okay, so we're either forcing the P-type silicon to go N-type, or forcing the N-type silicon to go P-type, which is exactly what happens when you turn a device on and off. Now, so here's our little spot here, and when we take it over in this direction, we see it disappears. So basically, that told me that what we were dealing with was an accumulation of N-type dopant in that area. Now, another neat thing that we got out of this image is when you look at our N-channel devices over here, we're actually turning those devices on. And conversely, over here on the other side, we're turning our P devices on. And I don't think anybody has accomplished that either. So again, first time in public these images have been seen. We just completed this work a few weeks ago. And this is kind of a description of what the actual root cause was. But what it was, a silicon defect, which caused an accumulation of dopants, which resulted in a short circuit in that device. And now I will go to my concluding remarks. The technology has come a long way. You know, from that 1 micron device where we looked at it with scanning Kelvin probe microscopy, you know, with that very noisy, coarse, giant image, to where we are now, looking at 14 nanometer fins. 14 nanometer fins and finding that defect site. Now, but still, there's so much work to be done here. You know, three-dimensional devices, I mentioned, you know, require three-dimensional analysis. Is the proper approach plan, view, or cross-section? We don't know yet. But we do know that the prep is going to be complex, labor-intensive, and time-consuming. There's a lot of room to develop to develop processes to expedite that. But right now, that's the only method that we've seen that actually takes us to the answer. Sample prep yield needs to be considered. And then on my last example there, SCM has shown success, but you know, like I said, there's a lot of development and optimization work necessary, you know, to make it a very usable process. I would just like to thank a couple of my colleagues, you know, especially these guys, I mean, who did that iterative, you know, remove a couple of atoms, look at it, remove a couple more atoms, look at it. And then I guess I will thank you for your attention.
Thank you. Thank you. We can take a question. Alan?
Very nice talk.
Thank you.
So you prefer scanning capacitance to SSRM. Is there a what's your rationale for that?
My rationale is we've got a lot of experience with scanning capacitance right from the very beginning. Actually, Jim Slinkman was a colleague of mine, and we worked together developing SCM into a more usable technique, while Wilfred was in parallel developing scanning spreading resistance. So our area of expertise was there. So we've kind of continued down that development path. Now, that's not to say that, I mean, SSRM definitely has a lot of strengths, and I know, you know, some of my colleagues in here have a lot of experience with SSRM, and that's certainly, you know, another potential possibility to solve the problem that we're dealing with here.
So atom probe didn't show the agglomerated cluster of dopant atoms?
Well, you know, the thing with atom probe is, yeah, would it have shown that? Yeah, it would have shown that. But we had one fin, okay? We only had one fin showing this problem. Okay, so I know the sample prep difficulty with atom probe. The sample prep yield is quite low. So first of all, the likelihood of successfully preparing a sample with that fin was very low. Okay, I think that the sample, and they've been battling with this for a long time. It's great if you've got a whole big array of devices, and you can say, okay, that one didn't work, that one didn't work. Okay, we're getting emission from this one's going to work, and you get a beautiful picture. But the other thing too is you're getting a chemical analysis. Okay, and one of the things that's important in you know, as you well know in the semiconductor industry is you know, chemical and electrically active are not necessarily the same thing. And here we're getting, you know, pure electrically active.
Thank you. It was a really important answer. Thank you very much.
You're welcome.
Okay. So we'll take just one more question, and then we'll have a break, so you'll have more chance.
Yes, sir.
That's a very amazing talk.
Thank you.
So you mentioned that each of the transistors only have about 8 dopant atoms. They have each about 8 on average of dopant atoms.
Yeah.
So then we'd expect some kind of statistical variation from device to device, right?
Absolutely. Absolutely.
In the
You know, because
capacitance image, would you expect also intensity variation that's statistical from device to device? And as you polish away, some of them may lose their dopant, and you should just see, like, I don't know, step size change in contrast, or
yeah,
you see that?
Yeah, and actually, I mean, great question, and this is with regard to, the fact that, the question was with respect that we've got eight dopant atoms in that device, okay, and what's going to happen during our sample prep, and is the device, are things going to change as we remove those? And great question, and that's, it's certainly something that we need to be concerned with, and that's part of the question marks that are up there. We just don't know yet. There's a lot of work that needs to be done.
Yeah. Okay, well, let's thank Phil again, and thank you for your talk.